Welcome back, everybody. After my recent video about the Boss CE2 chorus pedal, someone reached out with a question asking what are the main differences between the chorus pedal and the Boss BF-2 flanger. They have a similar architecture to the circuit, but the end result of the pedal's sound is actually quite different. So we're going to address that as we go through our circuit today. So I have here our schematic, and this is actually a factory schematic, so it includes all of the buffered bypass and all of those things that I usually don't draw up in a schematic. But because the schematic is kind of big, I figured that I would just go ahead and use it as is and not redraw it in its entirety. So before we get going, I'm going to just highlight what the main components of the circuit are. We've got one block, we've got this block, we have this block, this block, that block, that block, this block, this block. So this is all the audio path here. But then we also have our LFO. We have some controls that go with our LFO. And then we have our clock generation block for the clock driver for our BBD. So there are lots of different functional blocks going on in here, but as we go through each of them, we'll see that building on what we've done in the past, we can start to make sense of what at first is a very large, complicated schematic. And I'm not going to lie, this is a pretty complicated schematic. So let's start at the very beginning. Off of the input, we have an input buffer. This input buffer goes through a resistor and a capacitor. The capacitor is going to block our DC and it's going to roll off some of our low frequencies. We have a large value resistor going down to a reference voltage, so this is biasing the base of our transistor. And our transistor has its collector tied to power, and we are taking the signal off of the emitter. So this is an emitter follower buffer, unity gain, non-inverting. Okay, pretty standard. We have a DC blocking capacitor on the output side there. Next, we have this op-amp stage that looks like this. So this op-amp stage, if you remember from the Boss CE2 video when we were looking at the chorus and talking about BBDs, this is what's called the pre-emphasis filter. This is a filter that is designed to boost the high frequencies by several dB so that the high frequency content is much stronger than the high frequency noise that a BBD chip is going to produce on its own. It's a trick to help increase the signal to noise ratio so that we don't have a really hissy sounding delayed signal. On the output though, you'll notice that we have this resistor in parallel with a resistor and a capacitor, and that actually functions as a single pole low pass filter before going into this next op-amp stage. And we'll actually see here in just a little bit why they decided to put that in there. But the next stage is another op-amp stage here. And the important thing about this stage, let me actually erase that real quick so that we can get a better look at what's going into it here. Oh, get my drawing tool back. That didn't work. Let's see if third time's a charm. A little more careful this time. There we go. All right. So our signal is coming in on the inverting terminal, and we're biasing the op-amp up to VREF, and we have a signal that's going to be coming from this direction also. So this op-amp here is working as a summing amplifier. And in the feedback loop, we have a resistor that is helping to set our gain, but we also have these anti-parallel diodes here with a resistor. Now, you may take a look at that and think that having these diodes in the feedback loop is just like the Tube Screamer or the SD1 or any of those kinds of soft clipping overdrives. But what's really happening here, because we have this resistor in series, is that instead of actually clipping to create distortion, these diodes are actually functioning as a limiter. Okay, so that what they're going to do is they're going to keep our signal from getting too large so that we don't saturate the input of our bucket brigade device. Okay, if you remember from the DC2 video, the boss used a compander before the input to the BBD devices to make sure that we are limiting the dynamic range. Here, however, that dynamic range limiting is being done by way of these diodes in series with this resistor. Putting the resistor in series means that we're not going to really clip so much as we are going to limit the signal. And these values have been chosen specifically to work together to limit the signal to an appropriate voltage. On the output of that summing amplifier and limiting stage, we have a two-pole Sallen-Key low-pass filter here. In the Boss CE2, this is actually a third-order filter, which means it has a steeper roll-off of the high-frequency noise, but this is only a second order because it's going to also be rolling off the summed-in feedback that comes in. The extra order for the input from the guitar, though, happens with these components. Remember how I said that this is a single-pole low-pass filter? The reason for that is so that when we have this single pole combined with these two poles, that's going to act as essentially a three-pole filter. Okay, but this guy right here is rolling off the high frequencies so that we don't alias. This is our anti-aliasing filter. Once we go through our anti-aliasing filter, we have a DC blocking capacitor. And then we come to the input of the BBD, but you'll see that we have this VR6 bias. That's this potentiometer right here. And what this potentiometer does is this allows us to bias the input into the BBD so that we have an even swing of our signal going positive and negative. Okay? If we were to just put a static resistor in there, because of component tolerances and everything, we might have it biased wrong so that our signal looks super clipped here, and then a big long full extension to the negative voltage, or it could look like we have our upside looks really great, but then our bottom side gets like totally clipped off. Okay, so this bias trim pot there is what allows us to account for those kind of variances so that we get the swing of our input signal perfectly centered around between the plus and minus swing. So then we go into our BBD device. This does the delay for us. Now, if we're just coming in and doing a delay, how is this circuit any different from a chorus? Well, the real difference between a flanger and a chorus is in the amount of delay time that you have. They are both using a modulated delay line, but how long that delay is that you're modulating is going to determine whether or not you're getting flanging or if you're getting chorus. Okay, that's the first difference. There's a second difference we'll talk about in a little bit. But that first difference, where you have a super short delay time that you're modulating, results in an effect that we call comb filtering. Now, there are lots of different kinds of filters out there. We have low-pass filters, we have high-pass filters, we have notch filters, and we have bandpass filters as kind of our four basic types of filters. But if we were to take a whole series of notches and cascade them, we get something that is called a comb filter. Okay, and the response of a comb filter looks something like this. It looks very much like the teeth of a comb, where you have a notch and then it comes back up, and then a notch and it comes back up, and a notch and it comes back up. And this comb filtering results in kind of that kind of hollow whooshing effect that is characteristic of both flangers and phasers. They both implement comb filtering. The reason why the two effects are different, however, is because it has to do with how these notches are spaced. Okay, the spacing for a phaser is very linear, but for a flanger, the notches tend to get closer and closer the higher you get up in frequency. Okay, but this is what's called comb filtering. It's just a whole series of notches, and it gives it kind of that weird, if you will, sound that that those types of modulation result in. So that's where our biggest difference is. Very short amount of delay time through here that we're modulating is causing those notches in the frequency response so that we get that comb filtering. On the output of our BBD, we have a DC blocking cap here, but then we have another low-pass filter stage. Okay, this is our third order Sallen-Key low-pass filter. This is what's referred to as the Reconstruction filter, because every time we get signal out of this BBD, it's for a particular moment in time. And the BBD has a fixed number of buckets inside, and so the samples in time are being discretized, meaning that they're for a short amount of time, and then a fixed time later we get another sample, and then another sample, and then another sample. And when we string all of those samples together, that discontinuity between one sample and the next sample results in a lot of high frequency hash noise. And so we roll that off using a pretty aggressive low pass filter. Okay, I talk a little bit more about that in the CE2 video. Then on the output of our low pass filter, we then have this op amp stage right here. There we go. And this is another filter. Actually, I cut a little piece off there. Let me get that back. So this is another low pass filter here. This topology is an op amp based Sallen-Key filter with a little bit of extra feedback right here. Okay, so we're rolling off more of the high frequencies. Why are we rolling off more of the high frequencies? Well, these have two different corner frequencies. And with comb filtering, you can get a very kind of metallic, nasty high end going on if you're not careful. And so this kind of helps with that. Okay, so it's just another filter. Once we go through that filter, the signal does two things. The first is it comes into this op amp stage, which is pulling triple duty. So it is an output buffer. It is a summing amplifier where we're taking our dry signal from here and we are summing it in here with our delayed signal. But it is also our de-emphasis filter. So remember, earlier in the circuit, we had a pre-emphasis filter right here that is boosting the high frequency noise or the high frequency signal to overpower the high frequency noise inherent in the BBD so that we get better signal to noise ratio. But we don't want our signal to have all of that extra high end in there. So what we do is we undo it with this de-emphasis filter that actually is really just the inverse of this filter, so that if we were to stack just this filter and this filter, we would get a flat response. So that is the first thing that's happening with our output from this op-amp stage. The second is that we go through a DC blocking cap. We have a level potentiometer. It's set up as a voltage divider, and it goes through a cap, through a trim pot and a fixed resistor, and then it comes down and gets summed in to this op-amp stage where we take our dry signal and we're taking feedback from our delayed signal. This feedback path right here is what allows us to get that really super aggressive jet flanging sound where it's really aggressive and it sounds really bright and almost shrill in a way. That's by way of having this feedback. And in this path, this VR4, let me go ahead and clear out this line. VR4 is the external potentiometer with a knob that you turn for the resonance control is what they call it. Okay, it's the amount of feedback that comes back through the loop. But this fixed resistance and this variable resistance set kind of what the maximum value is going to be. So if we were to set our resonance to max, so there's none of this resistance getting in the way, we still need some amount of resistance because it's coming into a summing amplifier, and we are just limiting what the maximum signal level is that it's going to contribute into our summed stage. And so this trim pot is an adjustment that gets made just to make sure that it gets adjusted to make sure that you don't get into like runaway oscillations. Okay, you've got to limit the feedback so that you don't go off into really bad, crazy effects. With like a PT2399, sometimes that oscillation can be kind of cool. In a flanger like this, it will pierce your eardrums and it is not pleasant. So that gets us through our whole signal path. Okay, so let's take a little look at how we're actually doing the modulation, because if we were to just take a look at the signal path, this is just a fixed delay at this point. So we've got to change that. So our LFO over here is a pretty standard topology. This is the Schmidt trigger integrator topology. It uses two op amps here. Our rate control is governed by the series resistance between our two op amps. And what happens is that resistance will govern how quickly these caps are able to charge and discharge through this feedback loop that we set up here. Okay, so it causes an oscillation of caps charging and discharging, and it gives us a roughly triangular output shape. Okay, it's not perfectly triangular, but it's pretty close. And so there is our LFO. And once we have our LFO, we have a depth control on the outside. This is just another voltage divider control. And this voltage divider control comes out over to this point. But before we take a quick look there, there's another external control that is chained with it, and it is this manual knob. Okay, so what this manual knob does is it helps set what kind of our median or average delay time is in our BBD clock combo. Okay, so as you turn manual up, manual is going to change the reference that this lug of our depth pot has. So if you see that we have a voltage divider from our plus 9 volt supply here, as we put more voltage on the base here, then this resistance between collector and emitter drops. And when that resistance drops, then that means we're going to have a DC voltage that is going to be present here. So instead of shunting the signal from here to ground, it's going to see a variable DC reference on the other side here, which is going to change how much of this depth is actually going to make it over here. So that's how the manual control works. Once we have our signal coming from the output of the depth pot, it comes through a large resistor over to here where we have a transistor that is connected to power with a variable resistor, a trim pot, and a fixed resistor, and a fixed resistor here. And what actually ends up happening is that the LFO has no real effect on this whatsoever. This right here is actually changing the bias voltage level of the base of this transistor. So our LFO signal is wobbling, but this transistor and resistors and potentiometer is changing the static bias on this transistor over here on Q7. Okay, so if we were to think about it, our LFO runs through some level, which is this straight line, and what this voltage level is that our LFO oscillates about is going to be determined by the setting of VR7 here. So VR 5, 6, and 7 are all trim pots that are used during the calibration process to calibrate the performance of the flanger so that it performs correctly. But once we have the combination of this bias voltage and our LFO voltage on the base of this transistor, that is going to modulate the delay time of the BBD by way of our clock driver chip. Okay, so here's our clock driver chip, and if you remember, the clock driver frequency is set by connecting an oscillator between this pin and this pin of our device. And so we have a capacitor here. We have a resistor and capacitor in parallel onto the base of a transistor. And this transistor has one side connected to power, the other side connected to ground, and a polarity diode. So that what happens is that this oscillator is governed by the value of this capacitor and also by how it's charged and discharged by way of the resistance that is seen from these other components. Q7 is set up to act as a variable resistor, and its resistance is constantly varying because of our LFO that's constantly going up and down. So as this resistance is constantly varying, that means that the way that this cap is charging and discharging is constantly varying, which means that the clock driver IC is constantly changing its clock frequency that it's providing to the BBD. So the delay time of our BBD is constantly being modulated through that action of LFO plus a bias voltage onto a variable resistor connected to the oscillator pins of the clock driver IC. And so when we put all of that together, we get this fully functioning flanger. Okay, so it's not the easiest circuit in the world, but by no means is it something that a DIYer is incapable of understanding. What it really takes is just stepping back and trying to break these things down into their constituent components in such a way that we can understand each of them. So, you know, it's really just a matter of coming in here and saying, where can I draw my boxes so that I can break this down into parts that I can more easily understand. And that is really all that is going on here. We just happen to have a whole lot of these boxes in this particular flanger because there is a lot that's going on with it. But hopefully you found this video useful, and hopefully it gives you a little more confidence to be able to pull up a schematic. And if it looks a little intimidating at first, hopefully you don't just throw your hands up and say, oh, this schematic is too hard, I can't do it. But hopefully you can dig in and try and figure out what's happening in each of the different sections. Because, something like a buffer and a filter and a summing amplifier and another filter, the delay stage, another filter, filter and summing amplifier, conceptually that is not too bad. But the specifics of being able to take a look at it and figure out what's going on does take some practice, so hang in there, give it your best, and hopefully you'll be well on your way to creating your own designs and modifications and whatever it is that gives you the most satisfaction in this wonderful hobby that we have. If you found the video useful, I encourage you to subscribe if you haven't, so that you'll be notified when the next one comes along. But until then, thanks for watching and take care.